So in covering the nuclear chemistry chapter, it's probably a good bet that you haven't looked at the stuff from 1A in a while, so I usually like to review that. So this section is just a real short description of some of the major discoveries of nuclear chemistry and just some of the notation, the ideas, the average atomic mass. So let's go ahead and get started. So the electron was discovered or sort of characterized in the late 1800s by a scientist named J.J. Thomson, who was out of Cambridge University in England. After Thomson's discovery, the next major discovery that people usually talk about is that of Ernest Rutherford. And Ernest Rutherford did an important experiment known as the gold foil experiment, where he revealed the structure of the atom as having a nucleus. And the gold foil experiment is one of those ones you should probably remember. So I'll talk about that, and I'll go back and talk about Thomson and Moseley here in just a second. So in Rutherford's gold foil experiment, he had an alpha particle source. And alpha particles are actually helium nuclei that are a result of nuclear decay of heavier atoms, heavier isotopes. So what ends up happening is alpha particles are emitted, and they're allowed to pass through a gold foil. And when these particles hit the gold foil, what Rutherford, who was working actually under Thomson at the time, expected to see was the particles going straight through with minor deflections. And the idea is that they had at this point known about protons as something that Rutherford discovered, and then they knew about electrons, and they weren't sure what the structure of matter was. And so maybe the simplest construction would be to say you had here's the gold foil, positive charges and negative charges, right? And they're all interspersed within this material. So the positive charges could be like blue dots, which I now realize was probably bad on the blue background. And negative, red could be the negative charges. And they knew that these had to be neutral, so that matter was neutral, so they knew that it had to be positives and negatives that balanced each other. Well, what they discovered, and this is called the plum pudding model, because they also knew from Thomson's work that the electron had to be very, very small. In fact, Thomson's work was the first indication that there was a subatomic particle. Okay, so what they actually saw, though, was that most of them went straight through, like 99%, 9.9% of them. Oops, I left the 9 out. Went straight through, and they did that by using a detector that surrounded the gold foil, and that detector would essentially record a bright light every time a particle would hit the gold foil or go through the gold foil. So most of them went straight through and landed right opposite the alpha source, but a few of them were deflected, and a few were deflected almost in the backwards direction. And the only way they could sort of surmise that that would be the case was with whatever it hit had to have a lot more mass than an alpha particle. Now at this point, alpha particles were known to be relatively massive particles coming out of nuclei. And so the idea is whatever it ran into had to be really big, right? So if you run fast and you hit a wall, most of the time, unless it's a movie or something, right, you run into the wall and you bounce straight back off of it. And that's because the relative mass of the wall being anchored to the earth is much more than your mass. The result is you go backwards, the wall stays in one place. Okay, so that most of the particles went through was the idea that matter is mostly empty space. And what space was occupied was very dense and massive. And that eventually, this very dense, massive region in the atom was eventually become known as the nucleus, and the sort of a sketch of the nucleus. Now, having pointed that out, this has neutrons and protons in it. That's the way we know it now. At the time, they only knew about the protons, and neutrons had yet to be discovered. Now, if you remember, protons is the basis of the atomic number. And this was sort of discerned by a gentleman named Henry Moseley, who was a scientist in England at the time. But he got called away at the beginning of World War II, or World War I, and ended up getting killed. But before he got killed, he made the discovery that the charge of the nucleus, right, increments for the elements. So hydrogen had one positive charge, helium had 2, lithium had 3, etc., etc. So Henry Moseley is often attributed the discovery of the atomic number, which is the number of protons in the nucleus, and we normally give that the designation Z. Okay. Now, he was also going to be, in his mid-20s, one of the first, he would have been the youngest recipient of a Nobel Prize. But unfortunately, they don't award those things posthumously, so he didn't receive it. But most people speculate that in, I think it was 1917 or 1915, he would have received the award. Okay. The next discovery is that of the neutron. And I'm going to include a slide that has a little QR code on it that takes you to the story of James Chadwick. James Chadwick got caught up in World War I as well when he was a visiting scientist. He ended up coming back and working for Rutherford. And Rutherford, by the way, worked with Thomson. So these guys are all sort of related to each other academically. But James Chadwick has an interesting story because he got caught and was a prisoner of war for 4 years in Germany, and he didn't sit idle. He formed a science club of all crazy things, and then he wanted to study nuclear radiation still, right? And he wanted to set up a lab, and so he convinced the guards to let him set up a small lab, but then they didn't have a radioactive source. They didn't have a source of radioactivity to study. What Chadwick ended up doing is buying some toothpaste. He convinced the guards to buy him toothpaste because at that time, what it was believed, the newly discovered radioactivity was thought to have all kinds of magical health benefits, and you could buy toothpaste with either radium or uranium. It had a radioactive isotope in it, probably radium, I would guess. And they would use the radioactive isotope out of the toothpaste to do their studies of nuclear chemistry. And by the way, these guys are actually all physicists, just to make that record straight there. Well, anyways, in 1932, Chadwick did an experiment to try to identify the unknown particle that they were, or the unknown mass that they were not really detecting, but knowing was there, but not being able to sort of isolate it, and that turned out being the neutron. And so that's what gave us sort of this final picture of the nucleus, at least as far as chemistry goes, right? So the nucleus is composed of neutrons and protons. The protons are what give us the identity of the atom, but the particular nucleus, right, its mass is determined by the protons plus the neutrons. So I often write it like this. And so this sum became known as the mass number. It was known that the electrons had very little mass, and it's given this symbol A. So all the mass of an atom would be constituted of the protons and the neutrons, and all the mass of the nucleus was protons and neutrons. Electrons were believed to be on the outside of the nucleus. Okay, we refer to the individual particles in the nucleus as nucleons. And so we have something called a nuclide symbol. And the nuclide symbol is something you're probably familiar with from Chem 1A. It's when you write the element symbol, and then you put in the mass number on the top left and the atomic number on the bottom left. If there's a charge, which is really not part of the nuclide symbol, nuclide symbols are really supposed to be reflective of the sort of the state of a nucleus, and then the isotopic symbols are usually those for more chemistry related. So isotopes, when we talk about isotopes, we're talking about atomic and chemical properties, and nuclides, we're generally referring to nuclear properties. But for the most part, people sort of mix these things up in chemistry, although I'm sure the physicists are like driven mad by that, but it's probably okay. All right, so let's put some of this together. I have boron, right? So the atomic number is 5. And then I need to, if I wanted to, I could provide a mass number up here. Now, it turns out there's something called isotopes. And there was a gentleman named Aston who worked with Rutherford, right? And he developed the mass spectrometer, and it was actually the first person to show that elements of a substance, in his case was neon, actually came with different masses, and that mass was attributed to a different number of neutrons. So we have something called isotopes, and for boron, there's actually 2 different isotopes. There's boron with 5 neutrons. Let me write it like this: boron that has 5 neutrons. And there's boron with 6 neutrons. And together, right, all boron atoms have 5 protons. So 5 protons and 5 neutrons gives us a mass number of 10. But if we look at, for example, the other isotope of boron, which is boron, and then 6 plus 5, right, because there's all boron atoms have 5 protons, we get boron 11. Now, boron 10, and we'll talk about this in a second, but boron 10 and boron 11 have what we call exact masses. And for boron 10 and boron 11, they're very close to 10 and 11 because the mass number, right, represents the masses of protons and neutrons. And in boron 10, right, there's 5 protons, 5 neutrons, and each has a mass of about 1 atomic mass unit. Now, when you look, though, at the periodic table, what you'll notice for boron is you notice that the mass that's on the periodic table is actually 10.811, and there's actually 1 or 2 more significant figures if you dig into it probably, but 10.811 atomic mass units. Well, what happened, right? Why isn't it 10? Why isn't it 11? And it's because what we do to get this mass on the periodic table and make this mass useful is we want this to reflect the average mass of boron, so that when we get a compound that has boron in it, that it'll have the correct mass averaging the isotopes that are present in the sample. So naturally occurring boron sources have both boron 10 and boron 11, but it turns out boron 11 is 80% of that sample, right? Makes up 80% of the sample of boron that you get in nature. That results in an average mass of being about 10.8 because it's about 1 atomic mass unit more and reflects 80% of the naturally occurring boron. So these are what are known as average atomic masses. We'll talk about the calculation for that here in a second. And those are what you need to work with in a laboratory and grabbing like carbon sources or boron sources from the shelf, right? So, but when we're talking about atomic stuff, we're talking about nuclide symbols. We're actually going to be referring to what are called exact masses. That's the mass of boron 10 exactly and the mass of boron 11 exactly. Well, let's sort of put some of this into practice, right? So I have the nuclide symbol for chlorine 35, and if I want to know, I want to fill out this chart. Z is the atomic number, A is the mass number, E, I just decided to put it on here as the number of electrons. This is not something that normally shows up on a nuclide symbol, but chemists do it all the time. And N is the number of neutrons, right? So if I'm reading the symbol, number of protons is 17. Because it doesn't have a charge, it's neutral, the number of electrons would be 17. The mass number is 35. And then the number of neutrons is just, right, mass number minus atomic number. So when I do that, I get, I think, 18 neutrons, like this. Okay, so 17 and 18 make 35. 17, 18 make 35. Now, you could also be faced with something like this, right? And it's giving you an atomic number and a number of electrons and a mass number, and then you need to write the nuclide symbol. So what you do first, right, is you go to your periodic table and you find the atomic number 6. So atomic number 6, right, thanks to Henry Moseley, is carbon. Oops. Let's see where so this would be carbon. And then it's got a mass number of 13, so that actually just goes up here in 6. Now, the number of neutrons, which was left off of this line, right, would actually be 7. And then I'll talk about these columns here in a second. What element is this, right? So what I want you to do is go ahead and fill out the rest of this, and then we'll come back. When you come back, we'll discuss the rest of I'll have the numbers filled out, and then we can talk about what these numbers are for. So I filled in the rest of the information that was missing. Element number 92 was uranium, so I put U here. Notice I put a different number of electrons, and since you have more protons than you do electrons, it would be a +2 charge up here. And like I said, this is not normally what you put in a nuclide symbol, the charge, but it's kind of like what chemists do with it, so I figure it'd be important to show it to you. And then we have a 235 here, right? That's the mass number. And the way I got 235 was I hopefully added the atomic number and the number of neutrons together correctly and got 235. Now 82, 82. You can tell I did it wrong once, right, because I had the wrong number there. 82 is for lead, and lead 208, right, has 82 protons and then 82 electrons because it's neutral. I didn't put a charge up here. Since it has a mass number of 208, then I just took 82 and hopefully subtracted from 126 correctly. Or sorry, from 208 correctly, and I got 126. Okay, so this is what I wanted to show you, so you kind of understand a little bit more about exact masses and average masses. When you look at the periodic table, you'll typically see numbers like this, and I put a couple asterisks here to remind me to say a little bit more about this, but they'll say that chlorine has an average atomic mass of 35.453, right? And that's the number of grams per mole or atomic mass units. But if you look at chlorine 35, and you actually look it up, right? Chlorine 35 has this mass. It's much more precise than the average atomic mass. Again, carbon 13, right, has an average atomic mass, carbon has an average atomic mass of 12, but the mass of carbon 13 is 13.003355 when you look it up. Again, the mass of the isotope is very close to the mass number, right? And the other thing you should notice, though, is this is almost exactly 13, but here we're starting to see it's actually dropped below 35. And then if you get all the way up to here, for lead 208, there's actually a little bit more difference here, and uranium 235 actually ends up being just exactly 235. But there's an asterisk over here. Okay, so I'll talk about that in a second. All right. Now, why do these have differing amounts of precision, right? The reason for the differing amount of precision is variability of the isotope abundances even on Earth. So typically this is what you'll see for most elements, but you notice that lead 208 is got an exact mass of 207.97. The average atomic mass is 207.2, and there's only like 4 significant figures in this number. The reason it's that way is uranium is the sort of final decay product. Or sorry, lead is the one of the final decay products of uranium 235, 238. So when you think about uranium, right, we often think, like when we look at the periodic table, that this is the mass of uranium for like average atomic mass or whatever. But this is actually usually the mass of the most stable isotope. So it turns out that uranium actually doesn't have any stable isotopes, and the average atomic mass is really just trying to average the 3 most stable. Because this breaks up and gives us eventually lead, it lends itself to variability in the lead content that you find in samples. And so then you end up getting variable abundances of lead because of the sort of contribution from uranium. So the bottom line, though, is really what I want to talk about was these numbers that you see over here, right, aren't as exact as these simply because these reflect variations in abundance on Earth, and there's even more variation in abundance as you go out through the universe, apparently. So let's see, what else is there about this? Yeah, other things. Chlorine 35, right? The average atomic mass is 35.453. That's because there's another isotope, which is chlorine 37, right? And those two averaged together give us the 35.45. Carbon has carbon 12 and carbon 13. You notice the average mass is much closer to 12. And because there's only 2 isotopes, you can probably guess that carbon 12 is the most abundant of the stable isotopes. And then finally, like when we're looking at uranium, right, we talked about these numbers being funny. This is the mass for uranium 235, which is the less stable isotope, and 238 is the more stable isotope. So how do we calculate average atomic mass? So I'm going to show you how this is done. First of all, we use averages because every sample that you pull of an element on Earth in a compound or pure, right, is made up of different isotopes, each which have a different mass. And so what we do when we calculate the average atomic mass that you see on the periodic table, so like this guy, right, all these masses, those are just the averages of all the stable isotopes. If you notice down here on bismuth, right after bismuth, you start seeing a lot of them in parentheses. 83, atomic number 83, is the last element that has stable isotopes. So anyways, what we do to calculate the average mass is we use the percent abundance, usually generated from something like a mass spectrometer, and the exact mass of that isotope. Now, these could go on further. I just shortened it up just to make life easy for us. And this is the calculation that typically we do, okay? All you have to do is you do what's called a weighted average. And to get a weighted average, what you do is you say, well, 92.23% of this mass makes up the average, so you go like this. Just multiply them together. 4.67% is made up of this mass, and then 3.10% is made up of this mass. So what you're going to do is you're going to add all these together and get the total mass and then divide by 100, because percent is per 100. So when you do this calculation, you're going to have the average mass or the total mass of 100. And so you'll go ahead and add these up. Oh, and by the way, make sure this adds to 100%. But you'll add these three results up, get a number, and then divide by 100 to get the average atomic mass. So I'm going to go ahead and stop it, and then go ahead and when you restart, I'll have just the answer worked out for you. Okay, so there's the result. I just multiplied these all together, added them up, and just to check, right, this number needs to be between the numbers that make it up, because it's the average, right? But this, again, percent means per 100, so this is the mass of 100, so I divide by 100, and this is the mass, average mass, I should say. Average mass of one atom.